Okay, so up until now we've been looking at the Cartesian coordinate system, and now we're going to move on to look at the curvilinear coordinate systems, which are the spherical and the cylindrical coordinate systems. So we're going to first start off by looking at the spherical coordinate system, and I'm first going to draw my three axes, x, y, and z. And we're going to consider some point P, which is given by r, theta, and phi in the spherical coordinate system. So what are these? Well, r is the distance from the origin to that point P. Theta is our polar angle. That's the angle that this point P will make with the z-axis. And phi is our azimuthal angle. Phi is the angle that the point P will make with the x-axis. Okay, so with each of these, we can have our unit vectors. And of course, unit vectors are pointing the direction of increase. Okay, so the radial unit vector for r hat in the theta direction, it's going to be theta hat. Okay, remember it's pointing direction of increase. And for phi, it's the phi hat direction. Okay. So what are the limits for these? Well, for r goes from 0 to infinity. For theta, it's from 0 to pi. And for phi, is from 0 to 2 pi. Okay, so theta has to be from 0 to pi, otherwise you'll be counting each point twice. Okay. Now with each of these, we can also define our infinitesimal displacement elements. So in the r hat direction, it's given by dr. In the theta hat direction, it's given by r d theta. And in the phi hat direction, it's given by r sine theta d phi. Okay, so our total infinitesimal displacement vector then, dl, is equal to d r hat plus r d theta hat plus r sine theta d phi hat. Okay, now we can also write down our infinitesimal volume element, which is d tau, and that's just going to be equal to each of these multiplied together. So we're left with r squared sine theta dr d theta d phi. Now when we consider the infinitesimal surface element, we need to have a look at what side, that's determined by what side we're actually looking at. So let's take a sphere as an example. There are x, y, and z. We're going to look at a sphere. So here we're going to consider two surfaces. So we're going to consider one surface which is located at r is equal to big R, so it's located at the radius. We're going to call this one a dA1. We're also going to look at a second surface which is in the xy plane. Okay, this is going to be dA2. Okay, so what can we say about our first surface? Well, r remains constant at big R, so we have our little r is equal to big R, whereas theta and phi are changing. So our infinitesimal surface area element is going to be equal to dl theta L phi, and it's in the r hat direction. Okay. So here we obtain r squared sine theta d theta d phi r hat, or since we can substitute for big R, we have big R squared sine theta d theta d phi r hat. Okay, so that's for our first infinitesimal surface area element. Now what about the second one for dA2? So what we obtain here is theta, since we're in the xy plane, theta is going to be fixed at pi over 2. Okay, so here we have theta is equal to pi over 2. So our infinitesimal surface area element, dA2, will be equal to dl r, dl phi is in the theta hat direction, okay? Because r and theta are changing, or r and phi are changing. So with r and phi changing, we have now r sine theta dr d phi is theta hat. Theta is equal to pi over 2, so we're left with r dr d phi theta hat. And for the second surface, we would integrate between 0 and big R, and we would integrate between 0 and 2 pi for phi.